Renewables lie at the centre of the green energy transition, required to meet global net zero targets. New technologies are speeding up that transition, but one of the earliest, solar energy, still remains one of our most affordable and available power sources. UNSW Sydney's Professor RENATE EGAN joins us now to discuss how and why solar will play an increasingly important role in the future. Professor, it's wonderful to have you with us today. Thank you so much for joining us. Now, there is a huge amount of research underway on a global level about solar energy and its efficiencies. What are you most excited about right now?
I'm really excited about the success with deployment and integration. So we're actually getting an increasing amount of solar out there and deployed, and it's having a really significant impact on offsetting emissions. In addition, there's the future of the technology where we can see that continue to grow, and we can see the opportunity for continued improvement in performance, both of the solar cells themselves and the way that we deploy those solar cells and solar panels.
So on the materials side, RENATE, you are researching different types of materials to be used in these solar panels. What sort of a difference will these materials make?
Yeah, great question. The solar cells and panels that people know of today are made of basically material silicon, and they're limited in their maximum efficiency of around 25%. And that compares, for instance, with coal-fired power stations, which can convert the input material into energy at about 30 or 35% efficiencies. What we're looking at in the next generation solar cells have an increase in performance efficiency by adding an extra layer. So we actually create what's called a tandem, where we put one solar cell on top of another. So the base material underneath will be the silicon that we all know and love, and then we'll add another layer that will take us to efficiencies closer to 30%. And they're with a whole suite of new materials which offer great potential in improving performance.
So let's talk about the cell and the panel design. What does the future look like here?
Well, the conventional module, that we know now is so cost effective because it's basically the same thing as produced no matter what scale. You can do it in a 10 by 10 centimetre scale or a metre by a metre squared scale. And that has great utility in the big solar fields and in some rooftops. But we can see really interesting ways to change the aesthetics for rooftops. And we can see really interesting ways to change the way that we deploy the solar so that we can power devices remotely, sometimes under the skin, where we can keep sensors and blood sensors and the like going by illuminating through the skin. And in very interesting deployments in, for instance, bushfire sensing, where we can put a solar panel out there to maintain a bushfire sensor and communications in very remote locations so that we can keep lots of high deployment of lots of sensors and get lots of information.
These are really exciting types of innovation that you're talking about now. When it comes to the majority of them, I mean, how far away are we? What does a timeline look like to actually put this into practice?
Yeah, good question. So the technology we have today works, right? And it's really cost effective. The International Energy Agency recognises it as the lowest cost form of new energy generation. And in some places, it competes, even if you have a coal-fired plant that's built, with the cost of, particularly now with the cost of coal and gas increasing, the current technology competes even now. But we can improve and we can drive the costs down further. So by increasing the performance of the solar panels up to 30% efficiencies, that will drive down the costs further. The new applications in for instance, sensors and building integrated photovoltaics and vehicle integrated photovoltaics are actually happening now in small numbers, and we can expect those applications to grow.
Now, this is really important, of course, when it comes to circularity, but you're also very focused on the recycling of panels once they reach the end of their life cycle, their 25 to 30-year life cycles. Where are we at that front?
Yeah, so the University of New South Wales is already developing some innovative new technologies for recycling. So ways to extract, to separate the materials and to extract the different elements and the different components so that they can be effectively reused. The reality is that the rate of deployment of solar has been changing over the years. So there's a lot of solar deployed now, but it's basically doubled every 2 years. So if you go back even 10 years, there was not that much solar deployed. And the technologies are supposed to have a 25-year lifetime. So we're actually not expecting huge volumes of solar for quite some time, but we are developing the technologies, and the state and federal governments are supporting the early stage recycling tests and looking at logistics and how to deliver the recycling capabilities and to reuse the materials, again, in solar modules.